Hi friends, welcome back to Edupedia world. In the previous two lectures, we studied in details about the mechanical energy, the potential energy, the kinetic energy. We saw the formula, we saw the definition. In today's lecture, we will focus on the numericals regarding the potential and the kinetic energy. Let us get started with today's lecture. This numerical states that a bullet of mass 20 grams was traveling with a velocity of 500 meters per second. After traveling 10 centimeters in a wall, it comes to rest. So we know that the mass m is equal to 20 gram. The initial velocity, let us represent it as u, was 500 meters per second, and the distance traveled before coming to rest is 10 centimeters. Let us convert mass and distance into the SI units. 20 gram would be 20 divided by 1000 kg, that is 0.02 kg, and 10 centimeter would be 10 by 100, that is 0.1 meter. Now the first part asks us to find the initial kinetic energy. So A, the initial kinetic energy will be half mass times the initial velocity square, and that would be half times the mass in SI unit is 0.02 and the velocity is 500. The initial velocity is 500, so we write 500 square. Now if we simplify this, that would give us 5 into 500, and that is 2500 joule. So the initial kinetic energy is 2500 joule for the bullet. Now let us do the part 2. The part B asks us to find the initial momentum. Let me represent it by P, or let's say Pi, and initial momentum would be initial velocity times the mass, and the mass would be 0.02 in the SI units, this many kg, and the velocity is 500. That would give me 10 kilogram meter per second. So the initial momentum turns out to be 10 kilogram meter per second. Part C asks me to find the deceleration. Now where exactly is the deceleration taking place? The body is slowing down inside the wall, so we need to see the distance of 10 centimeter while calculating the deceleration. We have to use the equations of motion, but which one do we need to use? We know that v square minus u square is equal to 2as. Here we know that the final velocity is 0, that is the body stops. We know the initial velocity, and we know the distance through which the change in velocity is taking place. So using this relation we can find the deceleration or the acceleration A. Let's use this relation. So 0 square minus 500 square is equal to 2 times A times S in SI unit is 0.1. This gives us A equals negative 500 square by 0.2. That would turn out to be negative 500 into 500 into 10 divided by 2. So that's another 5. This makes it 125 with 4 zeros. A is equal to minus 125 into 10 to the power 4 meter per second square. So the acceleration is negative 125 into 10 to the power 4 meter per second square. The deceleration, that is the retardation, will be the same value without the negative sign, because deceleration by definition means negative of acceleration. So we get the deceleration. Finally, the numerical asks us to find the retarding force. So the force which causes the retardation is known as the retarding force, and that would be the mass of the bullet into the deceleration. So let me write mass into negative of acceleration. Now mass is 0.02, 2 divided by 100, that is 0.02, and the negative of A, that is the deceleration, is 125 into 10 to the power 4. This will make it 250 with 2 zeros at the end, that is 250, 25,000 Newton. So this is the retarding force, that retarding force which is applied on the bullet by the wall is 25,000 Newton. We saw in this question the need to convert all the units in the same system, and then we use the definition of kinetic energy, the mathematical definition half mv squared, to find the initial kinetic energy. We use the definition of momentum as mass into velocity. We use the equation of motion to find the retardation, and then finally we used Newton's second law, that is F is equal to mass times acceleration, to find the retarding force. Now let us see another example to understand mechanical energy better. In this question we are said that there is a ball which has a mass of 100 grams and it is initially at a height of 10 meters. From there it is dropped and the ball rebounds from the surface to a height of 8 meters. We are asked to find the initial and final potential energy, the initial and the final kinetic energy, and if there is a loss of energy, the reason for that loss. The mass of the ball is 100 gram. We will convert it into the SI unit, and that will be 100 by 1000, which is 0.1 kg. Height initial, I am writing it as HI, is equal to 10 meter. Now at this height, initially the ball is at rest, so the initial velocity is 0 meter per second. Therefore, the part A asks us to find the potential energy initial. Now we know the potential energy is represented by mgh. We are not given the value of g, so we will use the standard value 9.8 meter per second square. and that will give me mass as 0.1, g as 9.8 meter per second square, and h as 10 meter, which will be 9.8 joule. So the initial potential energy is 9.8 joule. Part B asks me to find the initial kinetic energy, KEI. We know that it is equal to half mu square. The initial velocity is 0 because it is at rest at the height of 10 meter. Therefore, the initial kinetic energy turns out to be 0 joules. Now the third part asks us to find the final potential energy. For the final potential energy, we need the final height, and the final height turns out to be 8 meter. And since at this height, the maximum final height, the ball again stops, because if it did not stop at that height, then it would go further upwards. So we can safely say that the final velocity, let me represent it by v, is 0 meter per second. Now the part C asks me to find the potential energy final, and I will use the same relation mgh. Now the mass is 0.1, g is 9.8 meter per second square, and the height, new height, is 8. Therefore this will be equal to 9.8 into 8 into 0.1, that is 7.84 joule. The final kinetic energy is half mu square, mv square, and v being 0, the final velocity being 0, the final kinetic energy is also 0 joules. Therefore we see that the total mechanical energy initially, let me write it here, ME mechanical energy initial is equal to 9.8 plus 0, that is 9.8 joule, and mechanical energy final is equal to 7.84 plus 0, the potential plus the kinetic energy, and that is 7.84 joule. So clearly there is a loss in the mechanical energy during the process. Now the question asks us to state the reason why there is a loss. There can be several factors contributing to the loss. When the ball is rebounding from the surface, a part of the energy is lost as heat and sound. So there is a loss in form of heat, loss as sound energy. Also there is air, and the air provides resistance to the ball. This air resistance also causes a loss of the mechanical energy. So there is also air resistance. So these are the main sources of loss of the mechanical energy of the ball. We see that this question helps us to see a relation between the potential and the kinetic energy, and helps us figure out that if there is a loss in the energy, it has to be attributed to certain reason which will cause the loss. Let us see another example before we close today's lecture. This Numerical asks us to find the work that has to be done on a 2 kilogram body. The mass is 2 kilogram. To provide it a momentum of 50 kilogram meter per second. And initially the body is at rest. So the initial velocity is 0 meter per second. The final momentum, the P final, is equal to 50 kilogram meter per second. We know that momentum final is equal to mass into the final velocity. Let me say it as V. Therefore, using this, I can find 50 is equal to mass is 2 kg into V. So the velocity, the final velocity, turns out to be 25 meter per second. The initial velocity was 0 meter per second. Now, using the work energy theorem, we know that the change in kinetic energy, that is the change in velocity, will be attributed to the amount of work done. So the work done is equal to change in kinetic energy. This is the work energy theorem in place. Now, how do I find the change in kinetic energy? It will be the final kinetic energy, that is half mv square, minus the initial kinetic energy, that is half mu square. For this particular question, the body was initially at rest. As a result, the second term turns out to be 0. Therefore, the work done becomes equal to half mv square, which is half times 2 times 25 square, and that is 625 joule. So we see that the work done to produce a momentum of 50 kilogram meter per second in the body of 2 kg mass is 625 joule. Now let us do it by a second method, that is the relation which we saw a while back between the kinetic energy and momentum, which was that P is equal to root under 2m and k. This is the second method. We know that the final momentum is 50, so we can write here as 50 is equal to root under 2 times the mass is 2 kg and the kinetic energy I need to find. This implies that 2500 is equal to 4 times kinetic energy. As a result, kinetic energy turns out to be 625 joule. Now this is the final kinetic energy, since P was the final momentum. But we already know that the initial kinetic energy is 0. This is the final kinetic energy. The kinetic energy initial is 0 joule because it was at rest. Therefore, the work done is change. Change can be represented by a delta of kinetic energy, which gives us the same result as 625 joule. So here in this question we see that we can find the work done either in this method, by this method, or by using the relation between momentum and the kinetic energy. Both will give us the same 625 joule result. So today's lecture we saw 3 different examples using which I tried to elaborate the relation between kinetic energy, momentum, potential energy. In the next lecture we will discuss about the conservation of energy, and then we will also see some questions regarding the conservation of energy. So till our next lecture, have a great day. Goodbye.